So, our first speaker is Tom Mitchell. Probably doesn't need any introduction. I'll just say, personally, he's one of the most inspiring machine learning researchers I know of. And I'm very happy and pleased to have him here and looking forward to your talk. Tom, take it away.
Let's see. Well, thanks to our organizers for doing this. It's really a great topic for machine learning. In my opinion, this choice of interactive learning is spot on for the future of machine learning. So if you want to think about the future of machine learning, I think all you really need to do is think about how humans learn, and machines don't yet. Because that just gives us a whole set of ways in which, obviously, there is some process feasible for doing learning. And machine learning has been very successful as a field, but it's kind of, let's say, over-focused its energy on one kind of paradigm. And so I think this week I'm looking forward to hearing about a lot of other approaches that involve more human-like and more interactive processes. So the particular variant of this that I want to talk about today is some work that we've been doing asking the question, well, if we had a sensor effector system like your phone that you would like to teach, then what would that look like? But you could think of a phone as a system that has a number of sensors, microphones, cameras, etc. A set of effectors. It can vibrate at you. It can speak. It can search the web. Some of these sensors and effectors are in the physical world. That is, it can vibrate, it can speak. But some of them are in the cyber world. It also has ways of sensing and affecting the internet. So the question we've been looking at as part of a project that actually Yahoo inspired. Yahoo gave a $10 million gift 2.5 years ago to CMU to explore the future of intelligent agents in mobile devices. And so the InMind project is what we call this. And we've been looking at a number of issues, but the one I want to focus on today is, if you could teach your phone things, what would you teach and how? How would that go? So it seems to me that if you think about most interactions you have with your phone, most of them are currently instantaneous. Like you might say, what's the weather? And it tells you. End of story. We never, you might repeat that conversation later, but there's no long-term nature to that. But there are a few things that phones do that, thanks to good programmers, are kind of conditional strategies that they're monitoring all the time. So for example, Google has given us a nice app that effectively achieves this function. Whenever I have to catch a flight, alert me to head to the airport so that I'll be there on time. I'm very pleased that Google engineers have given us this. But if you start thinking about it, you realize there are a ton of strategies you'd like to teach to your phone. And Google hasn't yet gotten around to it, or Apple, or the others. Here's one I like. Whenever it snows at night, wake me up 30 minutes earlier. I don't want to be late to teaching my class. If somebody sends me a picture containing my mom, send it to her. She loves getting those kind of things, don't we all? Whenever a student sends an email about a homework question, forward it to the right teaching assistant. Okay, now, these are all just common sense things, but only one of those is on our phone right now. And maybe you don't even maybe here in Berkeley you don't need the second one. But I bet you have your own. And I bet if you started thinking of phones in a different way, as something that you actually could instruct, suddenly you'd find that you have a lot of these kind of things. Furthermore, these are all in what I'll call the sensor effector closure of your phone, right? They're all, if you think about the ways in which the phone can sense the world and can affect the world, and then you leave open what kind of computer program is in there connecting that sensor and effector. These are all based on information that the phones can in fact sense and actions that they can in fact achieve. So why don't we have these things? Okay, so that's kind of the the idea that I want us to think about for this talk. So one way to think about this is, let's think in general about sensor effector systems. We'll assume that they begin with some set of sensors and effectors. They also begin with some primitive language capability. By that I mean they have a lexicon, a language that allows referring to each of those sensors and each of those effectors. Okay, and so for example, if I have an effector like, I don't know, sending email, then I want language in the primitive system that can refer to that effector and let me say something like send an email. Or if I have a sensor like accelerometer, then I want language that allows me to refer to that and say, what's the value of the accelerometer right now? And then some general learning mechanisms. I don't know how to fill that in yet. That's why I'm here to learn from you guys. But then what we want is we want a system that is going to be able to learn language, new lexicon entries to understand new phrases. Maybe I say, drop a note to Bill. If I say that to Siri or Google now, they don't know what it means. And that's reasonable. But what's not reasonable is that there's no way to tell it what it means. So the first time I say drop a note to Bill, I'm fine with the system not knowing what it means, but at least I ought to have an opportunity to teach it. We also want it to learn capabilities, of course. If it snows at night, wake me up 30 minutes early. We also want it to learn representations, long-term representations, so that we can have long-term discussions about things. You all kind of laughed when I mentioned the homework question should go to the right TA, but the only reason that's not within the realm of what we currently think about is because we don't have the ability to tell our system about new things. Right? Why can't I say, define the concept workshop, which has fields like title, location, time, and attendees. And by the way, one instance of a workshop is Interactive Learning 2017. Then, once it knew about that, I could give lots of additional sensor, well, I'll make this part of the stuff that's effectively another sensor. And now I can start giving instructions, teaching it strategies like whenever I'm attending a workshop, make sure I know how much energy I'm going to have to burn to walk up the hill to get to it. Or maybe more practical things. Okay, so those are some things we want to learn. So here's the outline. We just talked about the problem. I want to show you a very early prototype system which allows you to teach some kinds of commands. Then we'll talk about conditional strategies, if-then things, which raise some additional interesting issues, and a little bit on teaching by demonstration, and that's the outline. So our philosophy about teaching by verbal instruction is that teaching an agent should be like teaching me. Should be able to use natural language. Should be able to assume that I remember what you told me yesterday. Anyone should be able to do this. We want to make every user in the world into a programmer. Which, if you think about it, think about the fraction of people who can program computers today, it's a very small fraction. It would be very cool if we could get everybody who just owns a mobile device to become a programmer. We want to teach with a blend of verbal instruction and demonstration. We're not there yet, but I'll show you examples of each, not blended. And we want basically the user to do it anytime they wish. So simple criteria. And so, for example, in this little example, a person might say something like, tell Tom I'm late. And the system doesn't know what it means, but it should at least give you an opportunity to tell it. So let me show you a video. I have the phone with me, but I don't want to run the live demo, so I'm running the video. But afterwards, I'm happy to let you try the live demo. This is a screenshot of an Android phone. And I'll just play it, and you can listen. You have to listen carefully, because it's a computer voice. But Igor Labutov, who's one of our postdocs working on this, is the human voice that you hear. Whoop.
Tell Tom to come to the meeting a few minutes early.
Sorry, but I don't understand. Would you like to teach me? Say yes or just ignore.
Yes.
Great. When you say, for example, tell Tom to come to the meeting a few minutes early, what shall I do first? Either tell me what to do or say demonstrate to demonstrate.
Create a new email.
Composing new email, outgoing email, fields are, subject, body and recipient list. What shall I do next? When executing, tell Tom to come to the meeting a few minutes early.
Set the recipient to Tom's email address.
The recipient list field in outgoing email was set to tom@gmail.com. What shall I do next? When executing, tell Tom to come to the meeting a few minutes early.
Set the subject to please come to the meeting a few minutes early.
The subject field in outgoing email was set to please come to the meeting a few minutes early. What shall I do next? When executing, tell Tom to come to the meeting a few minutes early.
Send it.
I see that the message has no body. Email sent successfully. What shall I do next? When executing, tell Tom to come to the meeting a few minutes early.
That's it.
I'm currently learning the new command, tell Tom to come to the meeting a few minutes early. I'm trying to generalize to other similar commands. This takes several seconds.
Tell Bob to bring some coffee.
Composing new email, outgoing email, fields are, subject, body and recipient list. The recipient list field in outgoing email was set to bob@gmail.com. The subject field in outgoing email was set to please bring some coffee. I see that the message has no body. Email sent successfully.
Okay, so sorry for the crufty machine-to-human communication there. But what we just saw was Igor giving an instruction that was not comprehensible initially. Tell Tom to come early to the meeting. And then instructing the system by essentially breaking it down into sub-steps, right? So create a mail, add Tom's email address to the recipients, put this in the subject line. But then, interestingly, after he went through that, the next thing he said, tell Bob to bring the coffee, that was it. That was now comprehensible. So what happened there was the system learned two things. One is it learned a new language competence. That is, it learned how to parse, tell Tom to do something, which my postdoc loves. And second, it learned a procedure. Okay? This is how you tell Tom to come early to the meeting. You create an email, you put this in the subject. And that procedure is grounded in the sensors and the effectors of the phone. So what we have here is a language understanding system that can be trained, where the semantics of the utterances you make are grounded in the sensors and effectors of the phone. What it means to understand a command is to be able to create the code to execute on the phone to do that. So we also saw then that there's a kind of generalization that we get from Tom coming early to Bob delivering coffee. And that generalization comes in part out of the inherent structure of the semantic parsing that we're doing, and I'll show you some details on that. And it comes in part from some heuristics that we put in to kind of make it work as well as possible, and I'll show you those too. Okay, so that was the...
Question. If the generalization was somehow not perfect, how do you correct the system?
We don't yet have a good answer to how you correct it, and it certainly can make mistakes that way. So this is an early prototype. Like I say, I'm happy to let you try it out on my phone, but it's targeted in particular to learning. This one is targeted to learning commands where the unknown semantics have to do with phrasings and verbs. Like it didn't know the verb tell before, and now I can show you the semantics that it has for tell. But we haven't really done any significant work yet on error correction and those kind of, and even meta conversations, which would be interesting. Like you might say to me, oh, remember that time I taught you to how to tell Bob to bring the coffee. Here's something else related to, so we don't have any of that yet. Okay, so let's go back here. Okay, so the parsing that's going on underneath this is an important part of understanding what the algorithm is. It's based on a CCG parser, combinatory categorical grammar, the worst phrase ever for an algorithm, so CCG. But what CCG does is it parses expressions into semantic logical forms. And in the case of our InMind system, or LEA, we call it, our learning from instruction agent, those logical forms happen to also be expressions that can be evaluated. And when they do, they ground out in sensor effector actions available. So in CCG parsing, each parse step does both a syntactic and a semantic composition. So for example, if we have a typical grammar rule like an adjective followed by a noun can be parsed into a noun phrase, in CCG parsing we also say how to compose the logical forms for adjective and for noun into the logical form for a noun phrase. So an adjective, according to this, would act as a function that modifies the meaning of the noun. So I could have a car, or I could have a yellow car. A car such that color equals blue or yellow. And so each grammar rule tells us how to combine the meaning as well as the syntax. And then LEA learns from examples essentially by redefining its grammar. And in the case that we just saw, by adding a new lexicon entry for how to interpret the verb tell. Okay, so I'll go through a way too fast example just to give you the gist of this. But here, for example, I have an utterance, set the subject to time to go, which might come up if you're teaching it how to encourage people to get to the meeting on time. And what you see down here is that each token, according to the CCG grammar, has a syntax and a semantics. The notation is not that simple, but I just want to run through this to give you the idea. So for example, in a first parse step, the system might pick the token subject, which can be a field name according to the grammar. And then a field name turns into something with this semantics, which is grounded in the code of the phone. So if you mention a field name, that could be parsed into get the field by its name. Then we have this prepositional phrase over here. Well, any sequence of tokens can also be parsed into just a simple string. And so it is in this case. There's a preposition to that can, according to the grammar, absorb the phrase to its right, and then set can itself have a semantics, which can mean set a field from a string. So this, in the end, then, is the parse for that expression that we started out with. And notice every time I talked about applying a rule, instead of saying this will be parsed into this, I said this can be parsed into this. So it's a very ambiguous set of grammar rules. The three tokens, time to go, could be treated as a token sequence and parsed into a string, or it could be parsed in a much more fine-grained way. And so what it means to learn the semantic grammar in this case, is two things. It means to learn new rules, new parsing rules, new entries for new words that don't yet have an expression, or even additional rules for ones that already do. And the second thing it means is to learn the right control strategy for guiding that parse. And so what LEA is doing is actually learning both of those kinds of things. And so maybe if it sees the word set over here, it's more likely to treat the thing after the preposition as a string than some other kind of parse. Yeah?
So can this cope with like an arbitrarily large vocabulary size then?
In principle, it can handle an arbitrarily large sentence. We restrict it to sentences. In practice, it gets hard to do it for, it's a very explosive thing in practice. So the number of potential parses gets very high. And the way we learn the control strategy for the parses is we have an evaluation function, which is a learned log linear evaluation function. And then we do a beam search, keeping the 50 most highly valued parses along the way as we go. So if you make really complex sentences, the problem that hits you first is just the beam of 50 is not wide enough, and then you get into some serious complexity. Great question, though. Okay, so out of what we saw from that, oh, this is a slightly different example, I'm sorry. If we say, tell Tom I am late, then we get a parse. If you imagine the demo, instead of saying tell Tom to come early, you say tell Tom I'm late. You'll get the same kind of episode where you have to teach it. And then, as in that demo, basically the thing that it learned that's new is it learned the semantics for the verb tell. And it looks like this. So tell is, when you execute tell, it's going to be a function of, in this case, 2 arguments, where you do a sequence of steps, including creating an instance by concept name, and the green things are constants that it decided on. So it's going to create an outgoing email, and then set the value of the recipient list to something it's computing from another argument. And the arguments in this case are Tom and I'm late, so it's going to get Tom's email address. And oh, I'm standing in front of the other one, which is over here, set field from string. It's going to set the subject to I'm late. Now in the full parse, these were not variables. They went all the way down to parsing into these strings. But our learning algorithm for learning the semantics of the verb tell takes that entire expression. And that expression, by the way, was built how? It was built by actually just composing just by writing down the sequence of steps that the user gave when it defined how to achieve the command. So this is not, this is then a description of what the actual steps are that the user did. And now the parsing learning comes in because now we know that somehow this full expression means this, because that's what the user told us how we could achieve it. And so now we search around for a parse, one of the many possible parses of this, whose semantics actually is equal to this. And that's what we're looking at here, except that we've generalized it into adding 2 arguments. And the simple rule for generalization is anytime we see a text span, a contiguous span of text, that actually corresponds to a subtree of the semantic parse, then we replace that subtree by a variable. And in the particular instance, you can see the variable bound to this contiguous span of text. Okay? So that's maybe a lot of details to digest in a few minutes, but you get the gist of it. The key ideas here are, we know the meaning of the utterance because the user just executed it, and we wrote down what that was. It's this. That's what the user did. Now we look for a semantic parse that will generate the same thing, and then we generalize that semantic parse according to subtrees of the semantic parse that correspond to just contiguous strings. So that's the essence of the approach. Okay, so we tried this out. Oh, there's a question, yes.
Oh, I was just wondering if the machine can automatically learn the command like this, tell Bob to tell Tom I'm late.
Let's try it. I don't know. It might. I mean, we don't have recursion in the sense that you could say there's a new sort of macro effector that we just taught it, which is how to tell somebody something. That doesn't yet have a name in the system. So I bet if we run it, it won't work because the probability of actually getting that parse, the parse you have in mind, to be the one that it finds is low. Yeah, but great question. Yep.
So then if you taught it that command and it's added that parse into the subtree, if you wanted to do something like change the verb you were using, would it then go through that series of steps again and add something else to the subtree with the new verb, or is it able to link another verb to the same original parse?
Yeah, in the current system, you would have to go through, if I said, inform Tom that I'm late instead of tell Tom that I'm late, you'd have to go through the entire training experience. One of the beauties of natural language, which we haven't taken advantage of, is that in natural language you can go meta. You can say, oh, inform is a synonym for tell. And as soon as you say that, you and I get it, right? But we're not yet taking advantage of that. But I think that's one of the really interesting opportunities here. Yeah?
So I guess you're not using any distributed representation, like an embedding or anything?
No, not yet. Nope.
Symbolic.
This is totally symbolic, based on CCG grammars, which have been around for a while. And those are logical forms, right? The key thing about them, the logical forms, is not that they're symbolic, but they do have to be executable. And so if we use embeddings, we need some way of...
No, it would inform the probabilities, I think. The embedding.
Oh, I see. Yeah, we could do that. Jayant Krishnamurthy is the guy who's providing the CCG parser, and he's always moving forward on that too. So I can't say for sure there are no embeddings in there, but there weren't when we began. Yes?
Have you guys thought about, speaking of synonyms, but thinking of synonyms in the action space as well? So like sending an email versus sending a text might achieve the same goal. But currently you would have one phrasing that meant send an email and another phrasing that meant send a text.
Yep.
But if you start thinking of those as just informing, then can you do either one, or do you have to? Yeah, that's great. The answer is, I think the way you'd want to do that is you'd want a notion of a goal and a plan, and you'd say, well, just let them know, and that could be either by text or phone call or email or whatever. And then when you taught the next one, you could say, well, this is another strategy for letting one know. And we don't have that in the system. It doesn't yet have the notion of goals and sub-goals and alternatives or any notion of sophisticated planning. I think what you really want is a planner in there that you can talk about goals and sub-goals and alternative ways of solving them. Then it would be a much richer substrate for having this kind of conversation between the user and the system. We don't have that planner in there yet. Okay, I want to show you a few things, and I also want to give a positive training example of staying on time for time. Okay, so let me just show you a few other things. We ran some experiments with 123 people on Mechanical Turk. We gave them a text version of this system where we would give them instructions like, your 9th training task is to create a new email and set the recipient to the current email sender. Our system focuses on the email domain at the moment. And then we also said, don't type the email yourself. Use current email sender. So you give them some hints that force them to actually teach the system some intermediate concept. And then here in small font it says, the user says, set recipient to mom. Sorry, but mom is not an email address. Oh, set recipient to mom's email. The recipient list is outgoing email and was set to mom the best, blah, blah, blah. User says, set the subject to hello and send the email. It did it. User says, read the email. It does it. So here you see, as a result of, this is kind of a prototypical example we saw, and people were teaching new things like this.
effectively becomes an instruction when they say set the recipient to mom and the agent says I can't, then they say set the recipient to mom's email. That's a clarification which turns into now an opportunity to learn what it means to say set the email to mom. So in there we saw a number of little sub-strategies being learned, and on average we found that the subjects taught the agent new commands, like they would voluntarily teach it things like reply and things like this instead of spelling it out in more detail. They gained by doing that and saved some time by doing that. And some of them they were explicitly trying to teach, some it was just a side effect of the. And then here are a few more statistics. The most disappointing one was only 41% of our Mechanical Turk people actually completed the thing. So I think it was, that's a bad sign. But on average, they taught several commands. They did gain a lot from doing it. And some of them thought the system was sort of middle-ish smart. Yes?
So did the system start cold every time? So they're all teaching new commands. There was no iterative.
There was no accumulation of.
Although, you probably could get an estimate of the likelihood of accumulation as a function of duplicate commands that were taught by multiple people?
Yeah, I think there's quite a bit of overlap, at least for the kinds of tasks we were giving, because there's some common ideas that you and I have about email, like replying is an important primitive.
Sure, right. But were those predictable as a function of just the density of responses? I mean, could you have anticipated that in doing an iterative experiment?
I think we could. I mean, we're very interested in the question of how do you grab all this stuff from the crowd. There could be an issue because you might say drop a note means send a text message. I might say it means send an email. And so we could have our own individual dialects, and merging becomes kind of a question then. But I think if you look across many users statistically, you might be able to.
Well, I think this is where, where Rob's comment becomes especially relevant, right? Because it's like, customizing from a fully loaded system becomes much easier than drafting a dialect from scratch.
That's right.
Obviously, sure.
And we have different versions of the memory of the system that we're now playing with. Like one of them internally, we've already defined a whole bunch of people and their email addresses and little primitive stuff, and then we run some experiments just working off of that shared thing. And it's not that we have a documented lexicon somewhere that we all read. It's just that naturally these are the ways you would say those things, and it's safe to say them, it's safe to share. But then we have some other things where different people think drop a note means different things. And so there is an issue there of how you could blend in. Okay, so I'm going to, see we're halfway. I'm going to go through this next part a little quickly because I really want to get to the end and have some time for a discussion. But what we just saw was really about teaching commands. Tell Bob to bring the coffee. And then that turns into an executable procedure that can just be done. But if I want to go back to teaching really strategies that can be monitored, if-then kinds of rules, it's a slightly more subtle issue. So if I go back to these examples we looked at before, you can realize they're all templates of the form, if you notice something, then do something. And if you start collecting data on what things people give as conditionals, you see they roughly break into three categories. One is, for example, if I say, if I get a new email from Fred, then blah, blah, blah. That's one that you can teach just with language. I could say, test whether the value of the from field equals that. So that's one for which there's an intentional definition. In the mind of the user, they have a definition. They can impart that definition by language. On the other hand, the one that said, if it snows at night, wake me up 30 minutes earlier, that one's a little easier to convey as by demonstrating the procedure or articulating the procedure. Say, open up the weather app, read the current conditions field. If that's equal to snow, then yes. So that's a procedural one more than a declarative one. But the third one is the most problematic. There are a lot of ifs that you want to express that you really don't know how to articulate. If it's spam, don't show it to me. But none of us knows how to actually articulate what is spam. We can kind of say things. We can say, well, if it's trying to sell me something, it's probably a spam email. If it's from my friend, it's probably not. Some of those things, like if it's from my friend, for the system that's kind of partly observable, it might know a way. You could at least teach it how to estimate that. But if it's trying to sell me something, then... So we've been looking at that third category. It's probably spam if it's trying to sell me something. And we have some preliminary results which are submitted to a conference where we jointly learn. If I say something like, if the user says, if it's spam, then blah, 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 and then the system says, I don't really know what spam is, teach me, and the user says, well, I can't, but I can give you clues. So if the user says, it's probably spam if it's trying to sell me something, and we get a lot of these kind of statements, then we have an algorithm that learns jointly the meanings of these kinds of things, grounded in the details, the observable properties of the email and other things that can be sensed, and the values of those. We treat these as Boolean features, whose values are not really known. So it tries to learn the meaning of this language simultaneously with learning the values of this Boolean property for each email, simultaneously with learning the classifier to fit the labeled data we do have on spam and not spam. So it's kind of a three-way learning problem involving learning the parsing strategy for these things to ground out in the email observables, learning the values of this Boolean predicate for each email in the set, and then learning the classifier that actually says spam. Yes?
Are you really hoping to beat the regular spam filter, or it's like or are you seeing it like as an alternative to it, right? Because like a regular spam filter is less dedicated per user and more sort of a global feature. So here are you trying to get...
Oh, you mean spam is we all agree?
Right.
That's fine. Think of spam as just an example. I could also have somebody saying, instead of saying, if it's spam, then don't show it to me, they could say, if this is an email trying to invite me to something, be sure I see it. If it's an email trying to invite me, it's just another case where you cannot write down the algorithm. You don't have it in your head. If you could, a lot of people want that algorithm. But instead you can say, well, if it includes words like, you are invited, that would be helpful. And you could say other things. The point of this example is just that it's the type, the user's trying to define a Boolean concept, but they don't know an intentional definition of it. They don't have a definition, a hard definition. But instead they have this kind of informal, mushy things that they can say about it. And so what do you do in that case? And our response is to say, well, we want to learn a classifier over emails. Emails have a number of observable features, like the bag of words, for example. But they also apparently have some other features that we don't know how to get their values, but we have a sentence whose meaning is supposed to tell us how to get those values. So what we need to do algorithmically is we need to learn how to parse this into a meaning that's grounded in the observable properties of the email. Plus, we need to learn the classifier based on on both the observable and the unobservable properties of the email. And so the learning here involves an EM process, basically, to jointly learn these from what data? From data which is labeled examples of spam emails and not. And so then that's indirect information about what these things may mean if we know how to parse them. So it's kind of a chicken and an egg. Okay, so let me just zoom through this because I want to get to the third, just a very brief third thing, which is a video, and then we can open it up for a lot of discussion. So we ran an experiment where we got Mechanical Turk people to generate emails. There's always this privacy issue with emails. We paid people to generate emails of 7 types. Here they are. Like one of them is you're writing an email to yourself as a reminder to do something. So we had people generate 154 examples of those kinds of emails and others. Then we had other Mechanical Turk people try to teach this, just write down advice on how to classify emails into those 7 categories. So for example, some reminders will have a date and a time in the subject. Or emails from a public domain are not office requests. Things like this. So we have then that data set which allows us to explore this problem of trying to learn the meanings of these grounded in the email, along with from data about what are the category labels of the different emails that were available. And so what we found is that the system doesn't work perfect, but if you, in blue, plot the F1 score, the accuracy of the learned classifier in the end, versus number of labeled examples, and in using the sentences provided by humans, compared to just using the observable properties of the email, like the bag of words, with the same labeled email data, then in fact you do get considerable leverage in the early part of the curve, right? Where data is sparse, then the human advice, even though informal and unspecific, does ground out into features that the system assigns for itself and that are in fact helping with the classification. So this again is early work, but I think it introduces a kind of interesting question, which a category of problem, which is there are a lot of things we say to each other that aren't really formally write-downable. They're not really definitions. They're kind of hints to each other. And so the general template for this problem is I do have some labeled things. I have these documents that are labeled as, I don't know, self-reminders versus spam versus meetings. And then I have these features which are not really crisply defined algorithms. They're sentences. They mean something. You and I understand kind of the gist of what the sentence means. If it's trying to sell me something, if it's trying to invite me. And so the problem then is if we represent those features not as algorithms, as we typically do, bag of words, we know how to grab the words, but instead as these fuzzy sentences, then how can we learn an approximation to the meaning of those sentences, which is a good enough definition of a feature that it will actually improve the classification task in the end. So that's the template. And I think there are a lot of problems like this when you get into natural language interactive learning, because a lot of what we say in natural language is actually not something you could write down as a first-order logic expression. Okay, so let me show you quickly the third thing. This is some work by other people working on the InMind project, in particular Brad Myers and Toby Lee, one of our PhD students, and Amma Cesaria. And they've been looking at the complement to verbal instruction, which is demonstration. And I'll just show you I told Toby that please make me up a video that's 1 minute long. And he did by speeding up the video. So you have to watch, you have to watch fast. Here you go.
Order a cappuccino.
Sorry, but I don't understand. Would you like to teach me? Say yes or just ignore.
I'm going to restart because you missed that.
Yes.
Oh no, the video is.
Order a cappuccino.
Sorry, but I don't understand. What do you...
I'm sorry. Okay, I'm going to skip the video because something fried there. It wasn't playing the video, it was just holding the title. So instead, let me show you that what...
Order a cappuccino.
Sorry, but I don't understand. Would you like to teach me? Say yes or just ignore.
Yes.
Great. When you say, for example, order a cappuccino, what shall I do first? Say
Order a
demonstrate to
cappuccino.
demonstrate.
Demonstrate.
Whenever the user gives the agent a command that the agent cannot understand or doesn't know what to do, the user can teach the agent by demonstrating how to perform a task using any third-party apps installed on the phone. In this example, the user demonstrates how to order a cup of cappuccino using the Starbucks app.
Order a cappuccino.
Executing.
The agent learned the task and is now able to automatically manipulate the Starbucks app to order a cappuccino for the user. From only one example of demonstration, Sugarland can also determine the parameter in this task from the user's voice command and find all the other drinks it can order from Starbucks by analyzing the structure of the app's user interface. As you can see, the duck icon on the screen is now clicking on behalf of the user to order a coconut milk mocha macchiato. This work will appear in KAI 2017 and was supported by Yahoo through CMU's EMAC project.
Okay, so the point there is it's a quick illustration of some parallel research on teaching by demonstrating. And again, there's a generalization heuristic in there, which is if you're demonstrating an app that has a pull-down menu, for example, as the Starbucks app does, when the system is tracking your actions, it's looking at the other entries in that menu as candidate things to generalize to. So what we haven't done yet, but of course want to do, is build a system that will allow you to demonstrate when you feel like, just speak when you feel like, and to do both together. Because if you demonstrate to me how to order a cappuccino, you probably say, you know, now I'm choosing the way to pay. My default is my credit card, but if that's, you know, if you want, you can use PayPal. You'll tell me stuff if you're teaching me to do it. So you give me commentary while you're demonstrating. And we're not yet, we don't know how to do that yet, but we're collecting mechanical Turk data with people speaking while they're running, while they're demonstrating things. So we're at least starting to get some insight into what kinds of things people say. Okay, so with that, let me just end up with a few. Is this okay if I take another 2 minutes, or am I? Okay. A few points on where this might go. So of course, one research issue I just mentioned is we like to understand how to combine verbal with demonstration instruction. Share learning across agents. If I teach it something and you teach it something, then is it safe, or should we have some process for understanding when it's safe to add that to the global vocabulary? Incremental refinement. So when I said, if it snows at night, wake me up 30 minutes early, that's exactly the thing I want to teach the system. Until the first time then we started thinking about that. The first time it uses that, and it's snow flurries, I don't want to be woken up early. I want to be woken up if it snows enough to cause traffic problems on a day when I'm going to work, not on a Sunday morning. So I think a lot of human instruction is like this. Andrea and I were talking about this in the hallway, and I think she's going to tell us something about it in her talk. But the idea of when we think we're teaching each other, there's a lot not said. And humans have enough common sense to fill in some of that. Machines don't yet. Mixed initiative teaching dialogues right now, this one is pretty much one direction from the user to the system with a clarification question once in a while. This one is something we've been thinking about, which is related to this point, is maybe instead of teaching it, if you sent something, then do something, maybe you want to teach it, if it snows at night, then wake me up 30 minutes late because I don't want to be late at work. And if we include in the teaching the because part, that gives at least a starting point for the system to do some reasoning about what we really must have meant instead of if it snows at night. Well, and then in the end, I think combining both the kind of common passively acquired user knowledge that is very frequent, but combining that with ideas of demonstration and verbal instruction and experimentation by the system in whatever way can be most safe. And we need some new theory. And I think we're going to hear about that from people around here. But in machine learning, of course, there's a lot of theory on sample complexity. How many training examples do I have to show you to probably get you to learn something with a certain error bound? But what if we open that up to other kinds of communication between the teacher and the system? What if we assume these are user-picked examples instead of IID examples from some unknown underlying distribution? What if we assumed that the bit of information going between the user and the teacher is not a label, or could be a label, but it could be an instruction. It could be that kind of fuzzy sentences that I was showing you before. You know, if the email is trying to sell me something, then it's probably spam, and so forth. So example labels, demonstrations, suggested new features. This is another kind of advice. You know, if you think about an email, there are a lot of features of the email. There are an infinite number of features of the email that you could get by just tracking observable features like the sender, and then looking them up on the web and getting features of the sender. And the institution they graduated from also has a lot of features. And so they're effectively a grammar defining a nearly infinite set of feature sentences. And I think user advice about which of those features to use is going to be highly valuable. And you might think of it formally as a near infinite set of features defined by a grammar. You know, if you start at the email and you look at all the relations it's involved in and all of its words, then you get a grammar that can define an infinite number of feature sentences. And it's not a problem we look at much in machine learning because we always assume the problem comes to us with a nice definition of what features we're going to use to define the instances. But now that humans are giving us advice, that's part of the game, and maybe there's new theory to be discovered there. We also need a theory of agent architectures. We need answers to things like, what are the sufficient initial capabilities of an agent that would allow it to reach any instance of the agent that you want it to reach through instruction and experimentation and demonstration. Right? So you could think of an architecture as a template for a program, and you could say, well, this architecture, here's the Venn diagram of programs I could get to if I fill in that architecture with different parameters. Here's the starting point of here's what the system is initially, and it has these capabilities. Then you can think of learning as a trajectory through that space of programs, and we want to understand things about that trajectory. What are the sufficient initial properties that would allow an architecture to get to the final agent that we want it to be when it grows up? We want to know what's the value of a good curriculum in doing that. You know, as people, we learn to walk before we learn to run, before we learn to ride a bike. There might be something to that. What are sufficient conditions for non-damaging learning? I don't want my agent to start sending emails on my behalf before it's pretty good. And in the case of physical robots, it's an even bigger problem. So I'm going to stop there and just say the summary point of this, if you get one thing out of the talk, I think it's this in one sentence. Seems to me that because we've gotten into a regime where computers can actually understand what we're saying to some degree, and we're now all used to talking to computers, there's this huge new opportunity which is underexplored for having verbal instruction as a key part of what we explore in the field of machine learning. And when you open that up, you get into a number of interesting theoretical and practical questions. For example, the ambiguity of English and the incompleteness of instructions that we make to each other, and the need to deal with those kinds of issues. Okay, thanks. I talked too long.
Any questions? We had a lot during the talk.
So there's a lot of questions. So one is, how do you get permission to invoke all these different parts on your different agents on the mobile phone, for example?
Well, we have some very good people who've instrumented. The Android platform is much easier to work with than iOS. And Toby Lee, the student who made that fast video, is one of the geniuses underlying this. So the learning by demonstration system really is tracking every keystroke and every click that you make on the phone across every application. That stays on the phone, but it provides the kind of observability that you need for.
You have your own application, which this application is what follows you and opens up all the other ones.
Right. So the both of the demos that certainly the verbal instruction demo that I showed first is actually an app you can download on the Google Play Store. And that's how we're keeping all of our phones in sync as we just play with it. And our plan is to have half a dozen users by June, and there'll be people like me. There'll be the researchers. But then also part of the plan is to have maybe 20 to 100 users by the end of the year, just volunteers on campus to start getting more realistic understanding of how and whether people want this kind of functionality.
There's no easy way to do these kinds of experiments with Turkers, right? You can't ask them to download the app and do something.
Oh, we do that. We actually now have them, actually that's where they are running the app now on their phone. So it's part of the Turk job is to first download this software.
That's awesome.
Aditya.
So it seems to me that there's a related inverse question of how the machine can teach the human to interact correctly with the machine. Very much like students giving feedback to the teacher, that wasn't very good, you should probably do it this way. And for example, instead of just saying, I didn't understand your command, it could be I didn't understand your command because there are many Bobs and I didn't know which Bob you're referring to, or I couldn't parse the last part of the sentence, or something else, like in terms of giving feedback so that the teacher can learn the right unambiguous language in order to teach. So right now it seems like a lot of it was focused on how do we teach well, but how do we get good feedback so that how does the machine teach the human to interact in a way that it can understand easier?
I think you're right. That's a great point. We haven't been even thinking about that. Andrea?
Yeah, it's kind of related to mine. I mean, there was one interesting example that you had where it was like, send the email to mom, and then it was, I don't know what that is, send it to mom's email. So that was kind of an example of one of these sort of back and forths where, and I guess I have one practical question, just as how good is the speech recognition, and how is that a bottleneck? Because we have a lot of problems just with speech recognition, period.
Yeah, speech recognition is one of the bottlenecks. And one of the reasons why I showed the video instead of doing it live, because there's a 10% chance if I do it live, it'll misunderstand what I'm saying. At the moment, we actually use Google Speech, so that you can use it in a low volume rate for free, and you can pay a little bit. For these kind of magnitude of experiments, we could just pay for it. And it's pretty good, but one of the problems with Google Speech is you say an utterance, and then at the end you get back the whole thing. And we for some of the things we're doing, we actually want to track in real time the utterance. So at CMU, there are some other speech systems that we're experimenting with, but they're not as globally competent as the commercial ones, although they allow us finer grain.
So then it seems like, I wonder if you guys are thinking about making the speech recognition more of this kind of dialogue through your grammar, because it seems like you have the opportunity to do a lot better than just, here's a WAV file, what am I saying, because you have all of this logic around it.
Yes. So we're working with Alan Black, who has done a lot of work on speech and conversation stuff, and with Justine Cassell, who's done a lot of work on putting social norms into how you communicate back and forth. And so they're also part of the InMind project, developing more sociable speech conversational agent. And just beginning, actually, now we've sketched out an architecture to try to combine them, but we're not there. But we are planning to beginning to collaborate with some of this. There are a lot of social things going on. And, but I think, from my point of view, there's so much that doesn't work in what we're trying to do, even with crufty, robotic-like speech back and forth, that I'm happy to bring in those other issues, but I'm not sure they're going to simplify the problem.
So have you, it seems like, from the examples that you showed, both in demonstration and kind of verbal assignment, the clunkiest part was the human-computer interaction. I'm curious if you've thought about gathering other vague but informative signals. Like, for example, the computers that most people are using, certainly the phones of this low resolution, you've got kind of passive eye tracking possibility, so people are attending to certain things, they're looking at certain things. Have you thought about incorporating those into, so it's neither demonstration or explanation, but it's attention tracking, essentially. That could allow you to the system to ask the right, much smaller complexity space questions that it currently asks, or?
Yes, that's a good point. We've thought about that and even have there's a thing called OpenSmile, which is software that you can use that will do pretty close to real-time visual tracking from a phone. We have a version of that. But we haven't gone there because even though I think it's interesting, I'm not sure. I don't know how to incorporate it. And I feel like if we did, it would be down below number 10 on the list of improvements that would actually make this work. So there is information, whether you're looking at the phone or you're disgusted and looking away, or you're disgusted and looking at it. There is information there, but
it almost seems like it's high. It's either lower or higher, which is to say, at the level of. So I would say, conditional on already having a task, it's pretty low. But not conditional on that, which is to say, discovering what task it is that you're attending to, it would seem to be pretty high, right?
Yeah.
So,
good point. I think to say what are the top 2 or 3 problems that are the biggest problems. The number one is really language understanding. I mean, we're talking about having a conversation with somebody and grounding out the meaning in operational things that are going to execute on the phone. Our technology for language understanding is far from good for that. But, I mean, part of the experiment here is, given that humans understand that, can they actually break it down into pieces and define, how far will you be able to go with even limited complexity sentence understanding, given that you can train it, and so you can maybe subconsciously think of ways to do it. So, I mean, that to me is actually one of the big research questions here is how do you make language understanding really work? And maybe you don't have to have it work quite as well as people's language understanding if the trainer can build up something you want. Okay. Thank you.
I think we have a coffee break now, is that right? Yeah, so we have a coffee break and then Jerry's going to talk after the break. So.